Hey students, welcome back from spring break. Hopefully you had a good one. Wasn't too weird or stressful or anything like that. Um, we're here to get you guys going again, and today's topics are going to be erosion and unit conversions, which you'll need probably this Friday. So getting started, what you're going to learn today is that the faster the water goes, the more and bigger sediment it can pick up. Conversely, if it slows back down, it's going to start to drop that sediment back off. And this will affect the geographic shapes and features of a bunch of stuff caused by erosion. So we're going to look at like riverbed channels and deltas and stuff like that. Keep in mind too that erosion and things like uplift or volcanic intrusion, they happen at different rates. So we want to think about that as well. Last up, we're going to get a tutorial on dimensional analysis. Chemistry kids will remember this from stoichiometry. Hopefully they're either smiling at this point because it's a piece of cake, or for some reason, if they've got a mental block around it, they're probably like rocking back and forth, like, no, not again. Yeah, you thought you could escape. Nope, that is a lifelong skill I hope you guys all remember. And if you haven't had chemistry yet, no worries. We're doing some easy stuff, and I'll get you guys a crystal clear tutorial on this. So, getting started, I want you guys to go over these vocab very slowly and make sure you are extremely clear on what each of these words in green are. We're also looking at our new words presented there in blue. So at this point, please pause the video. You should have now paused the video. I'm serious. You should pause the video. Research studies show that students do not pause videos when told to pause videos. Hopefully you paused the video and actually went through each of these words slowly and methodically and wrote down any that you guys can bring some questions to office hours today. I'd love to see your faces, stop by, say hi, and I'd be happy to talk with you about any of these, get you as much detail as you possibly want and more. So yeah, check it out. Make sure you've got the vocab down before moving on. Okay, we're going to move on. Hopefully you paused the video and took the time to do this. Okay, so we're going to cover some quick examples here. We're going to go and get some visuals of this. Here's a great visual. All right, first up, if a certain amount of water passes through this river each minute, does it have to go faster to squeeze through the shallow zone, or once it's spread out? So imagine like trying to push a gallon of water through a big fat pipe, you can kind of just let it go through nice and slow, right? But if you want to get it through like a tiny nozzle, you got to shoot it through at an incredibly fast rate to empty the gallon of water in the same amount of time. So this is related to Bernoulli's principle to some extent, but basically water goes faster in these shallow channels than it does in deeper ones. Now we mentioned our learning goal today was about sediment size. So if the water is going faster up here versus over here, where is it going to be able to hold on to bigger amounts of sediment and also bigger sized pieces? The answer is it's going to be able to carry and transport sediment up here. As it slows down, it's going to lose its ability to hold on to those, and it's going to deposit stuff. It's going to deposit the big ones first. It's going to deposit medium ones second. Finally, the silt, the really fine particles, will settle down at the end. And what this means too is a couple things. Here, we'll get the animation playing. It's going to gradually fill in the deeper section with anything that it's been transporting from upstream. So this area is going to gradually get shallower and shallower. It can even get so shallow it becomes above ground, at which point you've got what's called a river delta. I want you guys to notice too that the really big pieces can kind of roll along. So get that view one more time. See, they can actually roll right along the bottom. They're not quite able to transport up over the top though, but you can pop them up and over because of the way that turbulence generates some extra drag right along across the bottom of the stuff there. So again, faster carries bigger and more, slower carries less and smaller, and the sediment is getting deposited in order of size there. Last up, check out this picture. Hopefully you guys see how this is a big old giant shallow zone. This is the result of sediment being deposited over a long time. This is that river delta we're talking about, and we'll be able to get some more thoughts on this coming up later. All right, next up, let's do this one. So we start with the smooth riverbed. As sediment gets picked up and deposited, it starts to build up these little roadblocks. On the front face of the roadblock, the fluid's traveling pretty fast to get over, and then the fluid speed stalls as it curls over the top of those. That means that stuff is going to get eroded on the front face and then deposited on the back face. And that's why these things tend to slowly migrate. This happens in the bottom of rivers. The place that you guys might be thinking about, though, is across sand dunes. Like, yeah, you've seen a sand dune move in movies and stuff. The wind picks up the sediment, blows them up and over the top. You can also see this on snowdrifts. up over the top of mountains and stuff. In fact, my favorite snowdrift is at the top of Taos, called the Ridge. It's a ski mountain in New Mexico, and it's basically like a 10 or 15-foot drop just to get off that. Like you're basically dropping off the top of the snow dune. And then after that, it's just an avalanche chute. It's like a double black. It's pretty awesome. Okay. So, yeah, pretty cool simulation. You guys can see what's happening. Overall, the drifts are increasing in size too, up to a certain point. Remember that this started out as a totally flat zone. Now we're getting quite a bit of contouring and shaping. And this is just because of the way that erosion works. Picks up stuff when the fluid's fast, drops off stuff when the fluid's slow. And it'll kind of gradually develop its own weird systems. Doesn't have to be limited to riverbeds either. By the way, when we say fluid, we mean gas or liquid. We mean any shape-changeable substance when we're talking about fluids in physics. It doesn't necessarily mean water. So you can get fluid erosion with wind carrying particles of sand too. And a great place where you might have seen this is the Arches National Park in Utah. Okay, I think we got one more here. Let me see if I can find it. Oh, that's not it. That's not it. That's not it. Hold on. Let's see. Oh, the YouTube one. This one's my favorite. And my cursor is going wacky. Let's pause this for just a sec. There we go. Okay, and I'm going to play this on double speed. You guys are probably doing that anyway. YouTube, the destroyer of attention spans. This is a super high-tech demo, by the way. Okay, so first demo is going to be ocean-based erosion. This is going to be from wave action hitting a beach, and this is going to be producing, well, I want you guys to predict what it's going to produce. You hit that thing with a bunch of waves, what's going to happen to the sediment that it carries? I want you guys to imagine the long-term result of this. And hopefully you're thinking, oh, this looks just like the West Coast. Like, in particular, like San Diego area, right? So you're going to get a long extended flat beach just underwater, and then you're going to get a cliff at the end of it. The cliff's going to eventually develop by caving in and collapsing. All right, jumping ahead. Now we're doing the wind-based erosion. We're going to include some different sediment size. When you get wind on there, which particles are going to move, which aren't? Going with the straw method. Yay, science. All right, hopefully you can tell you can roll some of the bigger sediment, but that it's the smallest pieces getting carried the farthest here. I don't think we're getting any dune action from this demo, but again, you can tell what's being transported and what's not, which matches one of our main ideas today. Okay, cool. Let's jump ahead. Next up, let's pause here for a sec. They're carving in a meandering channel. Okay, so channel is the shape of the riverbed. It's not the right shape or anything, but they carved in a meander, which is that curving zone. Now, they didn't need to do that. It turns out that the rivers will eventually develop their own meanders. They could have carved straight down the hill, and if they'd run this for long enough, it would have eventually built its own curves anyway. Now, that notwithstanding, let's talk about what's going to happen. Where's the fluid speed going to be fastest if they pour it up at the starting of the hill? It's going to be fastest when it's coming around the outside bends inside the channel. So like this bend, and then especially this bend. Where's it going to be slowest? It's going to be slowest after it's been dumped into this big flat zone. So what we're going to expect is for the most erosion to occur right here and right here. And what that's going to do is that's actually going to increase the size of the meanders. They're going to develop further. It's going to also etch a really kind of jagged V-shaped steep channel right there. Whereas down here, as it deposits, it's just going to develop a big, wide, shallow, flat zone, and it's going to dump the sediment as soon as the water slows down. So let's watch that happen. I want you guys to notice some detail here. You see how it's channel carving right there? See how steep that is? And we're also getting the most erosion, like right at these high-speed spots. It is moving the smaller sediment, not the bigger stuff. And right here, you can see it depositing. Some of the bigger sediment got deposited early on. whereas the finer sediment is able to travel farther. And it's creating just this big spread out delta system. All right, we're going to skip erosion of the mountain. That'll do it. Okay, so jumping back in, let's look at some river concepts in more detail here. First up, looking at this diagram, where are we going to have water speed going the fastest? And the answer is, of course, where it's steepest. So we're going to get high-speed water up here. As the ground gets more level, we're going to have water start to slow down. So next question is, where is the sediment going to get picked up? And the answer is, we're going to have lots and lots of erosion happening up here at the high-speed water, where it hasn't yet acquired a whole lot of sediment. Later, it's going to be saturated. Saturated means already carrying as much sediment as it can. So on one hand, it might be eroding some more sediment. On the other hand, it's probably dropping off some sediment. Those two ideas are balancing out in this middle stage here. And that means that it's transporting sediment without necessarily like picking up more material than it's dropping off. It's basically just carrying it downriver. Once we get to the slow stage, though, then it's going to have to start letting go of that sediment that it's been transporting. We're going to get deposition. It's going to deposit in layers. It's going to drop the big stuff first, the smaller stuff later. And it's eventually going to fill in any deep zones and extend out that shallow, just real mild riverbank all the way out. Okay, so next question is, what does the actual riverbed look like? And the answer is that a young, high-speed steep channel is going to be pretty vertical. It's going to be a sharp, jagged V shape. It's going to cut downward. At a more moderate age and steepness level, we're going to get more of a U channel. And then finally, where it's in an older deposition zone, we're going to get basically really, really, really flat, broad channel like that. So, cool website. I'll make sure to link this in classroom too. Question is, which of these, this is the correct 4 pictures, my PowerPoint's missing one. Which of these is the youngest river? Which of these is the oldest river? The answer is we're getting some new erosion right here. It was previously flat ground, and we're getting that steep, jagged V-channel etching. Here, that etching's continued to a much greater extent. Had some time for the terrain to recover and get some vegetation back on there. Now it's starting to deposit and get to a wider, shallower stance, so more like a U-channel. And it's also developing more meanders. Meanders are those zigzaggings back and forth. Here, the meanders have developed so far that they've even cut themselves out of the loop. This happens when a meander gets too big. Like eventually, this meander right here, it'll chop right through that zone, and it'll cut the old meander right out. And these riverbeds are extremely wide and extremely flat. It's a great website. Check out some more detail. You can read about any of the things we've been doing, some more example videos. Again, if you want to check some more stuff out, I'll make sure to link this in the Google Classroom site. All right. So that, I think, does it. We're moving on to unit conversions now. All right. Goal of unit conversions is that you guys can switch from one way of measuring to another way of measuring without making any math mistakes, without getting too bogged down in the setup. To do this, we're going to be using a strategy called dimensional analysis. We're going to switch over right now to second display capture mode. So cheers. Got a second webcam going. Pretty fancy. We're going to start out with a real easy problem. Let's say we have 3.5 feet. And we want to know how many inches it is. First of all, a foot is like this much, right? And 12 inches is like this much. And this is a foot, and this is 12 inches. It's the exact same thing. That's what it means to have a unit conversion. 2 ways of measuring the exact same thing. So you can write 12 inches per foot. By the way, hope you guys notice I'm writing these as square fractions, not as like, 12 inches per foot. See that diagonal way of writing fractions? That's going to confuse us. Don't do that. Keep them all nice and squared off. And what I'm going to be doing is first I'm going to list stuff out, brainstorm. This is a super easy problem, so you're like, come on, I already know what the answer is. But we're going to brainstorm stuff out. We're going to start with our given. If you guys are used to back solving in chemistry, you can do that too. That's fine. We're going to start with our given, and we're going to add on these unit conversions by multiplying. We're going to do so each time to try to cancel off the unit labels that we don't want, and then keep the unit labels that we do want. So I'm going to try to cancel off feet and keep inches by multiplying these two ideas together. To do that, I can use this one right side up or upside down. Do I want to flip this one over? or do I want to keep it the way it is so that the feet and feet cancel? And the answer is I want to keep it like it is. So here we go. We're starting out 3.5 feet. I'm going to keep 1 foot on the bottom so that feet on the top and feet on the bottom cancel out. Am I canceling off the units? Sorry, the numbers? No, just the unit labels. Okay, so at this point, inches is the only thing left, so I can put equals inches. I know that I'm done because that's the units that I wanted to end up in. I was answering the question, how many inches is that? And in the calculator, I can go 3.5 times 12 divided by, and actually don't even bother because dividing by 1 doesn't change the number at all. It's the same thing. So anytime you see a 1, just ignore it. But if it's a number across the top, multiply. If it's a number across the bottom, divide. You don't need parentheses. Just spam it all into your calculator all at once. And then let's see, 36, what is that? 42 inches. Cool. All right, so that was a sample problem. Let's do another one. Let's say I had 1.5 miles, and I wanted to know how many yards that is. First up, I can't remember how many yards to a mile, but I do remember that there's 5,280 feet in 1 mile, and that there are 3 feet in 1 yard. So there's some givens that I've listed. If you're not sure about unit conversions, you can always ask Google. It's great. It's an expert, and you can figure out those that way. Okay, so I'm going to start with my given. Again, if you're had chemistry, you know how to back solve these instead, that's fine. Next up, I want to plug in something that crosses off miles and gets me closer to my destination. I notice miles is right here. And one question is, do I plug this in right side up or upside down? Do I write 1 mile over 5,280 feet, or do I just keep it the way it is? And I'm going to keep it the way it is so that miles cross off. Miles and miles cross off. And now, if I put an equal sign here, I would get an answer in feet. How many feet are in 1.5 miles? But I want to keep going all the way to yards. So I'm going to put another multiply sign in. You can do as many of these in a row as you need to. One question is, do I want this right side up or upside down? And because I want feet to cross off, I'm going to flip this upside down. So I'm going to put 3 feet on the bottom and 1 yard on the top. Is it okay to flip them upside down? Well, remember, a unit conversion is the same thing divided by the same thing. So this really isn't any different. It's 2 ways of measuring the exact same distance. Anyway, feet and feet cross off. Yards is left. Yards is what I wanted. So I'm going to put an equal sign and put yards. And then I would grab a calculator and I'd do 1.5 times 5,280 divided by 3. And let's see, what would I get? 2,640? Yeah, let's go with that. 2,640 yards. Okay, cool. Let's do another one. Actually, let's real quick recap. What's the goal of dimensional analysis and how does it work? We're trying to convert between different ways of measuring stuff. What we're going to do is we're going to start out by listing our givens, making sure that unit labels are attached. That's what we're using to help set these up and identify what to do next. We're going to write them as those square fractions. We're going to look up some additional conversion factors, add them to our brainstorm list, and then we're going to multiply things together so that unit labels, not necessarily the numbers, but the unit labels cross off as we go. And in the process, we're going to make sure we decide, do we put it in right side up or upside down? That way we'll be able to cross stuff off effectively. And when we've got only the unit label that we wanted left, then we're ready to put our equal sign, put that unit label down, and grab a calculator. We're putting this all in the calculator all at the same time without parentheses. Any number in the numerator gets a multiply sign. Any number in the denominator gets a divide sign. And you can ignore anything that's a 1. Let's jump back in and do another sample problem here. All right. Let's say that we could walk at a speed of 5 meters per second. And what I want to know is, how many kilometers could I get to in a day if I just walked the entire time? So then my goal is to get to kilometers per day instead of meters per second. Well, first of all, meters to kilometers, kilo means 1,000, so there are 1,000 meters in every kilometer. Another idea that I know is that there are 60 seconds in a minute, and there are 60 minutes in an hour, and there are 24 hours in a day. Okay, so I'm kind of deliberately setting you guys up with a big one here, but this will be, I think, the hardest one we'll have to tackle for now. So I feel like I'm done brainstorming. I'm going to start with my given, 5 meters per second. That's the way we've been talking about speeds and velocities in physics. And multiply by, and let's take care of the meters to kilometers switch first. This one will do that for me. Do I plug it in right side up or upside down? And I want upside down so that the meters cancel. Okay, so if I stop right now, I'm in kilometers per second. Let's keep going though. I don't want seconds, let's convert to minutes using this idea. There are 60 seconds in a minute. And there are 60 minutes in an hour. So now I've got, let's see, minutes and minutes cancels, seconds and seconds cancels. So I've got kilometers per hour. That would be pretty useful for like the speed of a car or something. Let's keep going though. I also know that there are 24 hours in a day. I'm making sure to plug those in so hours and hours cancel. And now I've got kilometers per day. That's the idea that I wanted. So kilometers per day is what I'm going to plug in there. And then in my calculator, I would put in 5 times 60 times 60 times 24 divided by 1,000 equals, no parentheses, just plug it all in. Any number that's just a 1, you can ignore it. So again, that was 5 times 60 times 60 times 24 divided by 1,000, and that's the answer. That's dimensional analysis for you. You guys are going to be using this idea starting on Friday. And the reason you're going to be using this is because we're going to go figure out the speed of a tectonic plate. I have a strong feeling that centimeters per year is going to be a great way to measure those speeds. Okay, so I would suggest on Friday that you convert your velocities, whatever you find, to centimeters per year using the same system here. All right, that's about it for today. Let's just recap our goals here. Let's see. Our goals were to understand that the speed of a fluid affects the type of erosion that will happen, including how it picks up and deposits sediment. This changes the effect of streams, has an effect on the kind of, you can tell the age of something basically and the steepness. And that we're also doing unit conversions. Oh, I forgot one thing. I'm glad we reviewed. This is super cool. Okay, this one right here. So this is super relevant for me, for example, living in West Sacramento, which like Nokomis is a major flood zone. We have our own artificial levees, but there's also a thing called a natural levee, which is a really cool concept. So let's say this is the normal river, and then the river floods. The water during flood stage was going extremely fast in the river channel, in the channel. So it was picking up sediment, and that water is probably all brown and muddy and stuff, right? When the water leaves the channel and goes out to the shallow ground right here and starts to spread out, what happens to the speed of the water? It's going to slow down. At that point, it's going to deposit the sediment. So anything that it was eroding and transporting here is going to get deposited to the sides of the riverbank here. That way, when the flooding is done, it's left behind a natural levee, which is really cool. The rivers which flood will tend to make their own levee system over time. Now, does that save the adjacent farm or house? No. So not as good as a man-made levee, but it's pretty cool. One other thing I wanted to talk about is the idea of a setback levee, which is how some of the West Sacramento levees are being redesigned as they get maintenance done on them. Setback means that it's not on the riverbank, it's set back a ways. Why would you put a levee here instead of right here? Well, the reason is that if you put the levee right here and high-speed water is flowing through here trying to flood, it's going to be eroding that levee, and it's going to cause long-term maintenance issues or even possibly a levee failure. If you put it next to the high-speed water, it's going to suffer from erosion. If you set it back and you have this big flat zone here, this is low-speed water. If anything, this is depositing sediment, not so much eroding as actually depositing. And so by putting a setback levee, you've alleviated some of your long-term maintenance issues by manipulating the fluid speed next to the levee and whether the water is eroding or depositing. And in addition, there's a whole bunch of wildlife benefits to having this natural space right here that can be subjected to occasional flooding without any problems. So it's just good for the health of the river. Also, let's see, we talked about turning corners. Where is it going to be exerting the most force and causing the most impulse, which is force times time for impacts? Like, where's the water going to hit? Is it going to hit the inner channel or the outer channel if it had inertia and momentum headed this way? Answer is it's going to hit the outer part of the water channel. So the most erosion is going to happen on this side, not this side. And that's why the meanders are going to get bigger and bigger over time. That's why you'll go from a straight river all the way to a meandering river totally naturally. All right, that was the one thing I forgot from this lesson. Glad we reviewed. And I'll see you guys later, hopefully in office hours. Stop by. And again, please email me if you guys have any late work or need any assistance with anything.